Has the Riemann hypothesis, the most important conjecture about prime numbers, been proven? If not, how close are we to proving it? To be blunt, we are still a long way from proving the Riemann hypothesis. In fact, we have virtually no clue where to begin, and it's no exaggeration to say that there's little hope in sight. Why is this the case? Read on and you'll understand. Not long ago, a new Mersenne prime was discovered, marking the 52nd confirmed Mersenne prime. This prime number consists of over 41 million digits, surpassing the previous record holder by more than 16 million digits. The discovery relied on massive brute force computation, involving globally distributed computing resources and free software like the GIMPS project to execute complex algorithms. The study of Mersenne primes has not only advanced distributed computing technologies, but also deepened our understanding of number theory. The distribution of prime numbers remains a central topic in number theory, and Mersenne primes, as a special subset, are closely connected to several profound mathematical conjectures. For instance, the distribution of primes is intrinsically linked to the famous Riemann hypothesis, which proposes an exact formula for prime distribution based on the zeros of the Riemann zeta function in the complex plane. Proving the Riemann hypothesis would provide a robust theoretical framework for understanding the patterns of prime numbers and potentially unlock broader mathematical insights. In a previous video, I discussed the comparison of infinities and how Euler solved the Basel problem. If you haven't seen it yet, feel free to check it out. This time, we'll delve deeper into the remarkable contributions of the German mathematician Bernhard Riemann, specifically the Riemann hypothesis. This hypothesis builds upon and extends the Basel problem. Riemann, born in Germany in 1826, tragically lived only 40 years, passing away in 1866. From a young age, he exhibited extraordinary mathematical talent, even earning praise from Carl Friedrich Gauss, famously known as the Prince of Mathematics. Such recognition was exceedingly rare at the time. What's even more astonishing is that more than 50 years after Riemann's death, Albert Einstein was deeply inspired by Riemann's ideas while developing the theory of general relativity, showcasing how Riemann's insights transcended the bounds of time. In 1859, at just 33 years old, Riemann was elected a corresponding member of the Berlin Academy of Sciences. To express his gratitude for this honor, he submitted a paper titled on the number of primes less than a given magnitude. Though only 8 pages long, the paper is exceptionally rich in content and concise in language. It remains one of the most profound and challenging papers in mathematical history, continually inspiring and puzzling mathematicians. The paper's core ideas include the following. First, Riemann proposed that the variable s in the zeta function should be understood as a complex number rather than being restricted to real numbers. Second, he introduced the concept of analytic continuation. What is analytic continuation? Simply put, it extends the domain of a function so that it converges over a larger range of inputs. Using this method, Riemann defined zeta, 4 values of s less than 1. Third, through the study of zeta, Riemann provided a clear expression for the number of primes less than or equal to a given number x, with the only unknown being the location of the zeros of zeta. Finally, Riemann made a conjecture about the zeros of zeta, which became known as the Riemann hypothesis. Next, let's explain Euler's zeta function. This function sums the reciprocals of powers of all natural numbers. It's important to note that this series converges only when s bigger than 1. For s less than or equal to 1, it diverges and has no meaningful value. However, Riemann ingeniously devised a method to define zeta, 1 minus s, using zetas, thus extending the function to the region where s less than 1. Riemann's approach involved proving an equation through a series of ingenious transformations under the condition that s bigger than 1. This equation demonstrated that replacing with 1 minus s still resulted in the equation holding true. Based on this discovery, Riemann proposed the famous Riemann functional equation. Through this equation, the value of zeta, 1 minus s, could be calculated from the value of zetas. In this way, Riemann analytically continued the zeta function, extending its definition from the known values for s bigger than 1 to the region where s less than 1, only the point s equals 1 is undefined. How did Riemann come up with this formula? Apart from divine revelation in a dream, I can't think of any reasonable explanation for it. Additionally, Riemann extended the variable s in the zeta function from real numbers to complex numbers. The advantage of this lies in the fact that, in a certain sense, complex functions are simpler than real functions. On the complex plane, there are infinitely many directions approaching a single point. If calculations in all these directions yield the same result, this provides a very strong constraint. Functions that satisfy such constraints are relatively easier to handle. This extension by Riemann allowed for deeper study of the zeta function. Through a series of intricate derivations and proofs, he ultimately provided an expression closely related to the distribution of prime numbers. The only unclear part of this expression is the location of the nontrivial zeros of the zeta function. Let's revisit the title of Riemann's paper and one of its key concepts, the prime-counting function πx. This function represents the number of primes less than or equal to a given value x. For example, the number of primes less than or equal to 2 is 1, 2, so pi 2 equals 1. The number of primes less than or equal to 3 is 2, 2 and 3, so pi 3 equals 2, and so on. For the first 60 natural numbers, the graph of the prime-counting function exhibits a specific shape. If a simple formula could be found to describe the prime-counting function, it would allow us to quickly compute the value for any n. This would have profound implications, creating a significant impact on both theoretical and applied fields. You might wonder why Riemann obtained not pi x, but jx. However, there's no need to worry. As these two functions are equivalent in terms of information, they can be derived from one another. From this perspective, all the information about the distribution of primes is encoded in the locations of the non-trivial zeros of the Riemann zeta function. The relationship between pi x and jx can be expressed using the Möbius function. This function, introduced by the German mathematician famous for the Möbius strip, takes values of only 0, +1, and -1. The expansion above illustrates the first few terms of this relationship. Jx is an increasing function. As n grows larger, the nth root of x gradually decreases, and the corresponding d_n terms also decrease. Thus, in pi x, the contribution of jx is dominant. The main contribution to jx comes from terms closely tied to the locations of the non-trivial zeros of the Riemann zeta function. The real and imaginary parts of non-trivial zeros are often denoted by sigma and t respectively. Riemann proved that non-trivial zeros can only occur in the region sigma is between 0 and 1 inclusive. In the complex plane, this region forms a vertical strip of width 1, known as the critical strip. Due to the symmetry of the Riemann zeta function, the zeros are symmetric about the real axis. That is, if sigma plus it is a 0, then its complex conjugate sigma minus it is also a 0. Therefore, non-trivial zeros always occur in pairs. When we refer to the nth non-trivial zero, we typically mean the one with a positive imaginary part. The corresponding zero with a negative imaginary part is its pair. Moreover, based on Riemann's functional equation, which relates zetas and zeta, 1 minus s, we find that the zeros of the zeta function are symmetric about the vertical line sigma equals 1/2. Riemann computed the positions of several non-trivial zeros and found that their real parts were all equal to 1/2. For example, the imaginary parts of the first three non-trivial zeros are approximately 14.1347, 21.0220, and 25.0109, with all their real parts being 1/2. Based on this, he proposed a groundbreaking conjecture. All non-trivial zeros of the Riemann zeta function have a real part equal to 1/2. This is the famous Riemann hypothesis. The vertical line sigma equals 1/2 is called the critical line and serves as the center line of the critical strip. While all non-trivial zeros lie within the critical strip, the Riemann hypothesis goes further to state that they all lie precisely on the critical line. If the real part of a non-trivial zero could randomly take any value between 0 and 1, the probability of it being exactly 1/2 would be 0. Yet, Riemann believed this probability is 100%. If true, this would indicate the presence of deep mathematical principles underlying this phenomenon. Whether the Riemann hypothesis is correct remains an open question, as no universally accepted proof or disproof has been found. However, numerical calculations strongly support the hypothesis. Over 10 trillion non-trivial zeros of the Riemann zeta function have been computed, and every single one lies precisely on the critical line. As a result, most mathematicians believe that the RH is true. What is the use of the Riemann hypothesis? To illustrate its significance, let's consider a profound example. While exploring the RH, mathematicians derived an intermediate result. For instance, how many prime numbers are there roughly between 1 and 10 to the power of 100? This question relates to the distribution of prime numbers, a topic that fascinated the mathematical prodigy Carl Friedrich Gauss from a young age. In his leisure time, Gauss would carefully select intervals of 1,000 natural numbers and patiently count the primes within each range. This was his unique way of relaxing. It's evident that as numbers grow larger, primes become increasingly sparse. But how can this sparsity be quantified? Through extensive computations and careful comparisons, Gauss revealed the mystery of prime distribution. Their density roughly matches the derivative of the logarithmic function. In other words, the probability of a number near x being prime is approximately 1/logs. The surprising fruits of mathematical recreation. Gauss's discovery laid the groundwork for significant progress. Later, the French mathematician Adrien-Marie Legendre independently arrived at the same conclusion. However, their findings were based purely on numerical experiments and lacked rigorous proofs, so they remained conjectures, much like the Riemann hypothesis. This conjecture puzzled mathematicians for over a century. Finally, in 1896, Jacques Hadamard and Charles-Jean de la Vallée-Poussin independently proved it, establishing the prime number theorem, PNT. This theorem, crucial to mathematics. However, methodologically, the prime number theorem is merely an intermediate step in studying the Riemann hypothesis. States that the number of primes less than or equal to x, denoted πx, is approximately the logarithmic integral Lx. More formally, as x approaches infinity, the ratio πx divided by Lx approaches 1. When x is very large, Lx can be approximated as x divided by log x. Therefore, the prime number theorem can also be expressed as πx approximately x divided by log x. From the graph, it can be observed that as x increases, the ratio of px to both approximations approaches 1. However, πx divided by x divided by log x converges to 1 more slowly, while πx divided by Lx converges more quickly. Thus, as an approximation for px, Lx is more accurate than x divided by log x. If we describe it in terms of density, the probability that a natural number near x is prime is approximately 1 divided by log x. Similarly, the probability that a randomly chosen natural number less than or equal to x is prime is also roughly 1 divided by log x. Now, let's return to our previous question. How many primes are there approximately between 1 and 10 to the power of 100? Using the prime number theorem, we can calculate this. Let x equals 10 to the power of 100. Taking the natural logarithm, we get log x equals 100 times log 10 approximate 230.26. Therefore, the number of primes between 1 and 10 to the power of 100 is approximately x divided by 230.26, approximate 4.3924 times 10 to the power of 97. See how significant this progress is. The prime number theorem provides a foundational description of the distribution of primes, enabling us to understand their distribution more deeply. The Riemann hypothesis is a refinement of this foundational description of the distribution of primes. The following animation illustrates how the accuracy of the prime counting function improves as more of the non-trivial zeros of the Riemann zeta function are used in calculations. The more non-trivial zeros included, the more precise the graph becomes. All the information about the distribution of primes is encoded in the locations of the non-trivial zeros of the Riemann zeta function. As mentioned earlier, the Riemann hypothesis states that all the non-trivial zeros of the zeta function have a real part equal to 1/2. Mathematicians typically denote the real and imaginary parts of these zeros as sigma and t, respectively. The strip in the complex plane where 0 less than sigma less than 1 is called the critical strip, and the line sigma equals 1/2 is referred to as the critical line. It is known that all the non-trivial zeros of the Riemann zeta function lie within the critical strip. The Riemann hypothesis further asserts that these zeros all lie precisely on the critical line, with none outside of it. Primes are the atoms of numbers and one of the most fundamental concepts in mathematics. In this sense, the Riemann hypothesis can be seen as the code of the universe. Thus, we can understand the distribution of primes as follows. The prime number theorem provides a rough outline of πx in the form of Lix, but this outline is imprecise. The non-trivial zeros of the Riemann zeta function refine this outline. The more non-trivial zeros we include, the more accurate the refinement becomes. Inspired by the Riemann hypothesis, similar conjectures have been proposed in other areas of mathematics, representing extensions of the hypothesis and profoundly influencing the field. The Riemann hypothesis owes much of its public recognition to two prominent instances of publicity at the turn of 2 centuries. The first occurred in 1900 when German mathematician David Hilbert presented his famous list of 23 mathematical problems at the International Congress of Mathematicians. The 8th problem on the list combined the Riemann hypothesis with other prime-related conjectures, including the Goldbach conjecture and the twin prime conjecture. These 3 conjectures are exceptionally challenging, and none has been resolved to this day. The second instance came in 2000, when the Clay Mathematics Institute announced the 7 Millennium Prize problems, each carrying a reward of $1 million for a solution. The Riemann hypothesis was the 4th on the list. To date, only one of these problems, the Poincare conjecture, has been solved, and its solver, Russian mathematician Grigory Perelman, declined the prize. Despite these moments of exposure, the Riemann hypothesis remains significantly less well-known to the public compared to the Goldbach conjecture and the twin prime conjecture. This is because the latter two conjectures are straightforward to state and can be understood even by school children, whereas the Riemann hypothesis involves a far more complex formulation, requiring knowledge of complex analysis. Nevertheless, in terms of mathematical importance, the Riemann hypothesis is a higher-level problem than the Goldbach conjecture or the twin prime conjecture. This does not diminish the significance of the other two conjectures, which are both profoundly important and have challenged human intellect for even longer than the Riemann hypothesis. Professional mathematicians are keenly aware of the importance of the Riemann hypothesis. For example, when asked what he would most like to know if he were to return 500 years in the future, Hilbert reportedly replied that he would ask whether the Riemann hypothesis had been solved. Efforts to prove the Riemann hypothesis have been ongoing, but how much progress has been made? In short, a definitive resolution still seems far out of reach. In earlier discussions, we explored the significance and importance of the Riemann hypothesis, widely regarded by many mathematicians as one of the most crucial problems in mathematics. Although the Goldbach conjecture and the twin prime conjecture are more familiar to the public, the Riemann hypothesis occupies a higher intellectual tier. The question then arises, what is the current status of attempts to prove it? The answer remains that a complete solution is still a distant goal. Since 1859, when Riemann first proposed the hypothesis, some significant progress has been made. In 1896, Hadamard and de la Vallée-Poussin proved the prime number theorem. In 1905, German mathematician Mengelt demonstrated that there are infinitely many non-trivial zeros of the Riemann zeta function. In 1914, Danish mathematician Harald Bohr and German mathematician Edmund Landau proved the Bohr-Landau theorem, which states that for any positive delta, the proportion of non-trivial zeros that lie further than delta from the critical line is infinitesimally small. This implies that almost all non-trivial zeros are located within an arbitrarily narrow strip around the critical line. However, this result neither proves the existence of zeros on the critical line nor demonstrates that even a single zero lies there. An interesting aside is that Harald Bohr was the brother of the famous physicist Niels Bohr. Both were talented athletes with professional-level soccer skills. Harald Bohr achieved particular distinction, representing Denmark as a key player in the 1908 Olympics, where the team won a silver medal. Remarkably, during his 1901 doctoral defense, the number of soccer fans in attendance reportedly outnumbered mathematicians. On the other hand, Edmund Landau has no familial connection to Soviet physicist Lev Landau. Their only commonality is their shared Jewish heritage. In 1914, British mathematician G.H. Hardy proved that infinitely many non-trivial zeros lie on the critical line. However, the proportion of such zeros among all non-trivial zeros remains unknown. It could be 1%, 10%, or even 0. In 1942, Norwegian mathematician Adel Selberg proved that the proportion of non-trivial zeros on the critical line is greater than 0, a result that may seem modest to outsiders, but is a significant breakthrough in the field. If the zeros were distributed randomly, the probability of them lying precisely on sigma equals 1/2 would be 0. Riemann conjectured that this probability is 100%. While Selberg did not prove the 100% claim, he showed that the probability is non-zero, which was a major step forward. In 1974, American mathematician Norman Levinson proved that at least 34% of non-trivial zeros lie on the critical line. Remarkably, Levinson achieved this result at age 62 while gravely ill, passing away the following year. He later improved the lower bound to 34.74%, despite the minuscule improvement involving extraordinarily complex calculations. In 1989, American mathematician Brian Conry raised the proportion to at least 40%, and in 2012, Chinese mathematician Feng Xiaoji further increased the lower bound to 41.28%. This remains the best result achieved in this direction. However, even proving that 100% of non-trivial zeros lie on the critical line would not constitute a proof of the Riemann hypothesis. One could imagine a scenario where infinitely many zeros lie on the critical line, but a finite number lie off it. Any finite number divided by infinity results in zero. Alternatively, there could be infinitely many zeros off the critical line, but their size relative to all zeros could still yield a proportion of zero. Understanding such concepts involves delving into distinctions between higher-order and lower-order infinities, as discussed in earlier videos like From Infinity to Infinity. So, how might one prove the Riemann hypothesis? One approach would be to disprove it by finding a single counterexample. On the other hand, proving it affirmatively remains elusive. How can 100% definitively represent all? This question is still unanswered. Since scientists have already discovered 10 trillion non-trivial zeros on the critical line without finding a single counterexample, can we accept this conclusion as an axiom? Although the Riemann hypothesis has remained unrefuted for over 150 years since its proposal in 1859, and most mathematicians believe it to be true, we cannot accept it as an axiom. This is because the validity of mathematics stems from proof, not from experiments or empirical evidence. For example, in the process of studying the Riemann hypothesis, many intriguing phenomena have been uncovered. One such phenomenon involves the ratio of πx to Lx. Over a large range, this ratio is consistently greater than 1. Scientists have calculated this up to 10 to the power of 19, and it holds true. Moreover, as x increases, the absolute difference between πx and Lx tends to grow. For a long time, mathematicians believed that πx greater than Lx for all x. However, in 1914, the British mathematician John Edenser Littlewood proved that as x increases, there will inevitably be instances where πx less than Lx, and this sign change will occur infinitely often. The smallest value of x where πx less than Lx is known as Skewes number. This is an unimaginably large number. Current bounds for Skewes number have been refined but remain enormous, approximately between 3.7 times 10 to the power of 114 and 1.4 times 10 to the power of 306. Thus, 10 trillion zeros are not many but extremely few. Even large numbers like Graham's number, Tree 3, SSCG 3, and Sasquatch numbers, which are humanly created, super-large numbers, pale in comparison to infinity. In our universe, no physical change would require numbers of such magnitude. This illustrates the fundamental difference between mathematics and experimental sciences like physics. In 2018, Sir Michael Atiyah claimed during a lecture at the Heidelberg Laureate Forum in Germany that he had proven the Riemann hypothesis using concepts from quantum mechanics. However, he did not submit a complete paper to the mathematical community, which sparked some controversy. Given that Atiyah was awarded the Fields Medal in 1966 and the Abel Prize in 2004 and is regarded as one of the greatest living mathematicians, we probably need not worry too much about his reputation. Mathematics popularization is indeed a challenging task. As I delved into various sources, some mathematical concepts remained beyond my grasp. However, this process deepened my admiration and respect for the extraordinary scientists who lead us forward. To me, they are no longer just cold, distant names, but inspiring figures deserving of profound esteem.